Alright, so in this video what I'm going to do is I'm going to talk about many graphs that are involved in the study of motion. So far we may have encountered graphs from which we can figure out what the velocity is, and from the velocity graphs we could have figured out what the acceleration is, and so on and so forth. But I want this video to talk about things and quantities that we can derive just by looking at graphs. So it becomes very simple when we are just looking at, say, one dimension or motion in one dimension, that is simply, say, in one dimension like the x dimension in one direction, and using graphs that involve motion in one direction, we can evaluate terms like velocity, we can evaluate terms like displacement, we can also evaluate terms like acceleration. They become much simpler to handle. So to understand that, let me get rid of this for the moment, like so, and start with a very simple example and look at a couple of graphs before to figure out what those graphs intend to mean. So, like always, let us have our y and our x coordinates. Now, in our previous videos, we have dealt with graphs that have involved x and y coordinates, so something like this. So x here and y there. We showed motion of a body in two dimensions, the y and the x, by a plain simple line in the plane of x and y. That meant that this curvy line here represented a motion of a body. The body moves from here, there, so on and so forth in one direction, and we then defined coordinates of the motion of the body in correspondence with the origin. We defined things like position vectors of r as a form of t, and using those we defined displacement vectors between two position vectors like so, and which formed displacement vector s, or something like that. So we were defining motion in a 2D plane, but it becomes complex to understand what's really happening. So we try to limit our motion in 1D plane. So 1D plane or 1D line is simply a line in x. So we basically disregard what's happening in y, and we only consider motion of a body in x. But in actual physicality, what's really happening is the body is actually moving from here, there, or it may even come back to its own position. So it's basically moving in this direction. It's hard to look at what's happening in just the x direction. That is, it's hard to look at what's happening if we simply consider one axis, or say the x-axis, and describe what's happening in the position of the body. It could be here, it could be there, and things like that. What really helps though, if we define another coordinate axis called the axis of time, and we use the time axis to reorient it in the x direction, and we use the x coordinate in the y. That is to say that at different points of time, I'm going to plot what happens to the motion of the body at different times. So if the body was, say, at x equal to 0, if this is the center of the x-axis at time t, well, the body could have been there at time t equal to 0. Later on, at time t equal to 2 seconds, the body moved in the negative x direction and ended up being at x equal to negative 2. So to show that, what we would do is we will take the time would have been at t equal to 2 seconds, and we would correspond that t position with a negative 2 position in x. That meant that this height would be, well, 2 units. This length would be 2 units as well. So this would be the second position of the body. So a body could have, so the x and t graph would look something like this. Let me choose another color for better peel. So this is how the graph would look like. The body was initially at 0, then went down in x, continued moving down in x until it reached the point at t equal to 2, or 2 seconds. After 2 seconds from starting its motion, it was at negative 2. This position is negative 2, negative 2 units in the x, and this is where the body finally landed. Now, the body could have moved back in the x direction, like so, and to show that, we could have used another line that started from its original position, which was here at that time too, and say it took it, say, 3 seconds back to come to the origin. That is to say that if it were at x equal to 0 at t equal to 0 time, it was at this position at t equal to 2 time, it came back to this position at t equal to 5 seconds, or t equal to 5 units. That is to say, it took 3 seconds, 5 minus 2, or 3 seconds, or 3 units of time to cover this distance back. That is to say, if it were here, when it was at this position, it took an additional t equal to 3 seconds, or an absolute at t equal to 5 seconds, it reached back at the origin from here. So we could have said that the body's x versus t graph would have looked something like this. So this could have been the new graph. So our body's motion now, rather than having a curvy line like that, would be represented by this line here, which meant that the body moved in the negative x direction for the first 2 seconds and moved in the positive x direction for the next 3 seconds. 3 seconds here and 2 seconds there. So this is how x versus t graphs look. Now, it seems odd here that the x versus t graph in this case is negative. It's this V kind of graph that emerges. But in many cases, x versus t graphs could also look something like this, like so. It could be something like that, could hold constant, something like that, and could hold constant there. So what does an x versus t graph like this mean? Well, it basically means, let me get rid of this to avoid confusion for now. So if we take this graph here, and we look at the position of the body at time t equal to, well, let's call this time t equal to 0, as it is, because this is where the t coordinate crosses the x equal to 0 point, or the x coordinate. Let us call this time t equal to, say, 2 seconds. Let this be time t equal to 3 seconds. This be time t equal to, let's say, 4 seconds. And this be time t equal to 5 seconds. So the body is taking different positions in x, and the reason I say that is because these heights differ at different time periods or different time intervals. And what happens to the y coordinate, or here the x coordinate, because the x, or the distance coordinate, it points in the y direction. So initially, say the body was at x equal to, let's say, 5 meters, which is this length or this height. Finally, it came down to x equal to, say, 10 meters. Further on, it went all the way to 0, so this position corresponds to x equal to 0 position right there. It held that position for this 1 second, and then moved back to x equal to 5 in the next second. So this is what's happened to the motion of the body. Let's try to figure out what's really happening and where is what happens to the velocities in this situation. So from analysis, what we know is that, well, velocity in our 2D system, or our 2D plane, is given by, well, instantaneous velocity happens to be d of r of t by dt. That is the rate of change of the position vector with time. In our case, however, the position vector is not of the form x of t I cap plus y of t j cap, because we assume that the y coordinate is irrelevant, or we are not really bothered about it. So what we do in those cases, we assume that the y motion is 0. So our new, so this was the case in 2D. In our new 1D situation, the position vector happens to be just x of t I cap. This is our position vector, which is rightly so, because if this is our position coordinate, x coordinate here, then the body is only moving in this direction or in this direction. So these vectors here would be the position vectors, or which would be the same as xt I cap. So this is how you would represent motion in 1D. Now, with this definition still in hand, what we can do is we can reduce it from a 2D situation back to a 1D situation just by substituting this as the value of the position vector, because now this definition of position vector excludes whatever is happening in the y coordinate. So let's do that. That gives us d by dt of xt I cap. So basically, the velocity vector happens to be d of xt by dt I cap. Now, this gives us some very special properties. First of which, we see that the velocity vector happens to always point in the I direction, or in plus or minus I cap direction. That is, it could point here. Let me use another color. It could point here. The velocity vector could point there at some time. It could also point back there at some other point of time, because they all will always point in either plus x or minus x direction. That's because this is just a constant, but the direction is specified by this I cap. So the velocities always come out to be either towards the origin or away from the origin. origin being this central point here, or basically in the x direction, plus or minus. So that comes out as the position of the direction of velocity, which is very strange because in our 2D motion, the direction of velocity could be this, could have been that, could have been that. It's not really dependent or as simple as this, as in this case, where the velocity is only point in plus or minus direction in the I direction or the x direction. So that comes out as a special property of 1D motion. So we know where the velocity is always point. It is always towards or away from the origin or in the x direction. What about the magnitude? The magnitude is given very simply as the derivative of the x function with respect to time. Now, what is this x function with respect to time? That tells us this function here is basically answers the question, what happens to the x coordinate when we vary time? And to figure out what that means, we can basically look at what's happening in this system or in this graph here, because this graph is basically representing this line here, which is nothing but the x function as the x function as a function of time. So this white line here is x of t, because it gives us different x values at different t values. This is how you define a function. That means our velocity in 1D plane happens to be the slope of this function. A slope is something that tells us about how the line is oriented or how the graph is oriented. Here, the slope involves straight lines and hence just involves their orientation. So our velocity depends on the angle at which individual line segments of this graph at least are placed and would always correspond in the I direction of the motion. So to further understand what that means, let us evaluate what the velocities would be at different time. So in the first segment of motion involving motion from t equal to 0 to t equal to 2 seconds, well, in that case, the velocity vector would have been, well, the slope of this segment, the slope of this red line at that point. Because if we only consider the motion from t equal to 0 to t equal to 2, the body moves from 5 to 10 meters in that time instant. And therefore, the velocity would be the slope of that line. And slope is given by the difference in the y coordinates. The y happens to be the x coordinate here, that is 10 meters minus 5 meters, divided by the difference in the x coordinates. And the x coordinates here is given by the time. And the time is measured in seconds. So that means it would be 2 minus 0, 2 for the final position, 0 for the initial position, in seconds. This gives us 5 by 2 meters per second, or 2.5 meters per second. But this gives us the magnitude of the velocity. So we know that the body is moving with 2.5 meters per second as its speed, or basically this quantity. What about the I direction? Is it positive or negative? Well, because this value here is positive, the velocity would simply be this multiplied by I. And therefore, we know that the body is therefore moving away from the origin, away from where we started measuring its motion. So that is to say that if we had a coordinate axis like this, the x direction in which the body moves, the 1D case, and so this were the origin, we know at time t equal to 0 the body was at 5 meters. So this is where the body is at t equal to 0. At t equal to 2 seconds, the body was at 10 meters. That meant the body would have moved in this direction. It would have moved from here to there, to there, to there, ultimately culminating in its motion at x equal to 10 meters when the time struck 2 seconds. So this is what it meant by its velocity. So therefore the velocity vector would be in the plus I direction, which is rightly given by this, and the magnitude of that velocity vector would be 2.5 meters per second. So there we have it, the velocity for this case. Let us write that down. That's 2.5 meters per second in the I cap direction. What about its velocity in the second half, or the second part of its motion? So let's consider this part here. Well, in that part, the velocity vector would have been, again, the slope, because the slope is dx by dt. The slope is measured in terms of the difference in the y coordinates divided by the difference in the x coordinates. Very simply, that means the final position of the x coordinate, that is 0 meters, because at time t equal to 3 seconds, the body is at 0, minus the initial position, which was 10 meters. Now divide that by the time interval over which we are measuring it. That's 3 seconds minus 2 seconds. That gives us negative 10 by 1 meters per second. But this is a vector here, but these terms are just scalars. To account for that, we must multiply it by the I cap vector. So that gives us negative 10 meters per second in the I cap direction. So what does that really mean? That means that the body finally moved from here back to the origin with a negative velocity, which it should have done, because the origin therefore lies in the left-hand side to this position. So the body would have to move in this direction with a velocity of negative 10 meters per second in the the negative I cap direction, or 10 meters per second in the negative I cap, or minus 10 meters per second in the I cap direction. That is to say, it moved to the left. So that's how you also incorporate signs with velocity. So this is how you would measure the velocity in this part of the motion. What about this part of the motion? Well, in that part of the motion, we know that the velocity would therefore have been the difference in the y coordinates, or the difference in the displacement positions. At both these two time intervals, the displacement has been 0 meters minus 0 meters, because they both lie at x equal to 0. We divide them by the time interval, which is 4 seconds minus 3 seconds, and that simply gives us 0 meters per second. That is to say, for the next 1 second of motion, the body held its position at the origin. So the body was here at time t equal to 3 seconds, and it remained there for until time t equal to 4 seconds. So that is how we have a velocity at that time interval. What about the next one? Well, the next one still gives us another velocity. Then this velocity here is it would be the difference in the x coordinates again, which is 5 meters, divided by the time interval, which is 1 meter, 1 second. Therefore, the velocity here is 5 meters per second in the I cap direction. So back to a similar case as what we started with. So just by looking at the graphs, we're able to know that when the x-coordinate increases over an interval of time, in this case, when sloping upwards, the velocities are positive. When it's sloping downwards, the velocities are negative. When it's not sloping at all, the velocities are 0. And again, when it slopes up, the velocities are positive. So that is how we make sense of the x versus t graphs. So if we go back to a very generic example of what happened, and try to tabulate what's really going on in that case as well. Say the motion of the body was a more complicated motion like this. So let us divide this motion of the body into many parts like that. Again, this is your x-coordinate, this is your t-coordinate, this is still one-dimensional motion, and let us analyze what's happening to the body in these intervals. So in the first interval, we see that the x-coordinate always increases with increasing time, until this point where it slopes to a 0. So what happens in this motion? Well, in this motion, the x increases. That is to say, throughout its motion, in this time interval, the velocity would have been greater than 0. That's obvious, because x is always increasing with time. What about the next motion? Well, the next motion is a bit more special. Here, the x-coordinate always decreases with increasing time because it goes down. And this is to say that the velocity in this case would be 0 throughout this interval of time. What about this part? Well, this part again, the velocity, the x-coordinate increases with time, and that is to say that the velocity would be greater than 0 again. In this part of the motion, however, the body held a constant x-coordinate throughout its time interval. That is to say, this line is neither sloping up like it did here, or it's sloping down like it did there. It's holding a constant slope, and that slope is 0. So that means that the velocity here is 0. That is to say, this is what the motion would look like for a body at rest. So that's how you make sense of x versus t graphs. To account, now that we have accounted for the signs of velocities, we can also account for the magnitudes of velocities. The magnitude, as I've already stated, is given by the derivative of the x function as time, that's x of t by dt in the I cap direction. So that is how you measure velocities. So it's very simple. If the slope is positive, velocity is positive. Slope is negative, velocity is negative. and the slope is 0, the velocity is 0. The velocity happens to match with the slope because it's defined exactly as the slope of this curve, whatever it may be at different time intervals. So there you have it. That's how you make sense of x versus t graphs. There are many more graphs to come. In this video, we basically dealt with x versus t graphs. There are other graphs of the form v versus t, like velocity varying in time, and we also have graphs of acceleration versus t, or acceleration changing with time. We can figure out many more things by those graphs as well. So I hope this video helped you. I hope it made sense, and I hope it led you to believe that x versus t graphs are a much better way of understanding what happens, rather than just looking at the motion in actual x coordinate at different time by plotting those dots in different time or something like that. So this is how we basically make sense of the physical world, by plotting it as graphs. And I hope you understood the connection between velocity and the slope of a function like this in x versus t plane. So all the best and have fun.